Welcome to the video key for exam 1. So in the first question, we have a question about the total collision rate. And if we think about the collision rate, we know it's a function of the gas density and the speed of the molecules, the relative speed, and the collision cross-section. So the answer doesn't really depend on whether or not we have alike molecules or unlike molecules. Let's just go with molecules that are identical. So if we've got just one type of molecule and we're interested in the collision rate within that one type of molecule, so it's the density squared times a half. If it was between two unlike molecules, we just have the density of each one times each other and then without the half. The collision parameter for that gas and with itself and the relative speed. Okay, so looking at this, we can say, are any of these things affected if we lower the temperature and we keep the pressure constant? Okay, so if we lower the temperature and we keep the pressure constant, we know that's going to result in a decrease in volume. Okay, so we can write V is equal to nRT over P, and so we can see that since the temperature went down, the volume's going to go down too, since the pressure was constant. And so the gas is going to get more dense. And so this term is going to increase. It's going to increase in proportion to the temperature decrease. So if the absolute temperature goes down by a factor of 2, the density goes up by a factor of 2, and then we're going to end up squaring that in this equation. Collision cross-section, essentially insensitive to temperature. What about the average speed? So remember, the average speed is a function of the square root of the, we've got the temperature, we've got the reduced molar mass, so I'll write this as mu with a line over it to reduce molar mass. We also have the constants 8 and pi, although those aren't going to play a role in deciding what the trend is here, right? All we care about is that if we lower the temperature, that the relative speed goes down as the square root of that change. So notice we have a minor decrease in this term, the relative speed, but we have a major increase in the density, right? Because we're in this term, because in this portion, because it's the density squared. So I'll just underline this twice. So for instance, so we have a square root decrease, but then we have a squared increase. So overall, the collision rate is going to go up because our gas is going to get more dense as we decrease the temperature. 2, probability distribution has been normalized. What does that mean? And this means that if we integrate over all possible speeds, we have to say that there's a 100% chance that the molecule has one of those speeds, right? So if we integrate any kind of distribution function and we integrate over all space, and for speed distribution, it would be integrating from 0 speed to infinite speed. That has to equal 1 for the function to be normalized, right? You're saying there's a 100% chance of that particle having some speed. Number 3, compare the Maxwell distribution for argon and helium, and what's the difference? So if we plot these, we'll see that we have, if we have a gas that's light, it tends to be, so we'll put V for speed here, and this is going to be the frequency of finding molecules at that speed, that we tend to have some molecules be quite fast, and the average is faster than so this would be a light molecule. And if we have a heavy molecule, we know that it tends to have a much lower speed. Okay, so we certainly know that looking at this, helium is lighter than argon, so we expect argon to have a narrower peak, and it's going to be higher. And how do we know it's higher? Well, since we don't have a lot of area for this peak out at high speeds, and the areas under the curves, if they're normalized, have to equal to 1, then we've got to have a taller peak. So taller and narrower, so heavy and light. So it's possible to have a slow helium molecule. It's also possible to have a fast argon molecule, or I guess atom, I should say, for both of them. But overall, we expect that on average, the argons are going to be at lower speeds and the heliums will be at higher speeds. Okay, the next problem is very similar, except for looking at temperatures. And so the graphs are really going to look the same, right? We're going to have a narrow, tall peak and a broad, wide peak. And at higher temperatures, you're going faster. So this would be high and this would be low. So for the higher temperature, we expect it to be shorter, and we expect it to have a narrower distribution. Sorry, we're talking about the higher one, aren't we? A shorter peak, which is broader. Yeah, because we're talking about the high peak, about the high temperature. Number 5, place an ideal gas into a volumetric flask, replace the stopper, we raise the temperature, what happens to the total collision frequency of the gas? So this one is similar to the other one, but not identical. So let's go ahead and write out the relevant equation here, right? We said that we've got the density, the number density squared. We've got the average of the reduced speed, and then we have the collision cross-section. Okay, so looking at this, what happens when we raise the temperature? So raise the temperature, we know that this, we already said, we've got 8RT over pi, and then the molar reduced mass. And so clearly if we raise the temperature, this is going to increase. But it's going to increase with a factor that's square rooted, so it's going to increase pretty slowly. What about this term? Well, we put it into a volumetric flask and replace the stopper, so the volume is not going to change. The number of moles of gas is not going to change. So in this case, the density doesn't change. We can't change the density if it's a constant volume process. So all of this is unchanged. So really, the only thing that's changed is this, and we just said it when it increases. It increases slowly, but it does increase. So there's our answer. 6, which gas phase reaction would have the largest steric factor, P? So P, if we remember, it's a function of how hard is it to orient, right? So if there is easy orientation between the two things, then P would equal to 1. And if it's hard to get them lined up, then that would be P much less than 1. Okay, so remember the P factor accounts for the fact that not every collision, even if it's violent, even if it's a violent collision with plenty of energy to overcome the activation energy, not every collision can be effective if there is a requirement for the way the atoms are arrayed in space relative to one another. So looking at this, the bottom one, now all of these are going to have P's that are much less than 1 because we've got two stick-shaped molecules that react. And if we have a collision like this, we can see that's not equivalent to a collision like this, or a collision, we can imagine them having a side-to-side collision. Okay, so depending upon the way bonds are formed or broken in a molecule, not all of these are going to be equally effective. Some might be totally ineffective. Typically in molecules like this, this would be sort of what you're shooting for as an end-on. But notice, for the bond reaction, every end-on-end collision is equivalent, right? So we have 4 different ways of doing this. We can take this bromine and flip it over, leave the chlorine alone, or we could flip the chlorine over and then attack it with a bromine from either end. So there's 4 different possible end-on collisions that are equivalent. Whereas if we look at the other ones, because the molecules are heteroatomic, the worst one would be A, right? Because if you have end-on collisions, you could have an HH collision, you could have an HBr collision, you could have an HCl collision, or you could have a BrCl collision, right? So you could have, and not all those are equivalent. So only one of those is going to give you the reaction you want. So the largest steric factor would be reaction 6. All right, number 7. So looking at this, we have to find the heat capacity, and it seems like an ideal case to use the equipartition theorem. So we've got, let's find the internal energy first. So U is equal to 1/2 RT times the number of, in this case, the total number of modes. And we don't have to worry about whether or not to include vibration, because this is argon, so there's no vibrations. So in fact, all we have is translation, right? We don't have any rotation or vibration. So this is going to be 3 times 1/2 RT is going to give us the value for the internal energy. And so notice this actually will give us the internal energy per mole. So let's just write that there. And so if we take the derivative of the internal energy with temperature at constant volume, that will give us our CV. So take the derivative of this expression, we end up with 3/2 R, and as the molar heat capacity. So we plug that in, we get 3/2 times 8.314 joules per mole per Kelvin, and that comes out to about 12.5 joules per mole per Kelvin. And if we go to NIST and look at CV bar for argon, we'll see that it's really close to 12.5. That's an excellent estimate. All right, now calculate the rotational energy for a single oxygen molecule at 350 Kelvin. So we're just looking for one type of energy. Okay, so we know that U rotation is going to be, and we could do this on a molar basis and then divide, or we could do it on a molecular basis and just go straight there. So let's just do that. Let's just do it as a molecular basis. So we're going to be using Boltzmann's constant instead of R. So we have 1/2 kT, and this is times the number of rotational modes. Okay, so if we look at this, this is an oxygen molecule, so it's a linear rotor. So there's 2 different axes of rotation, right? We could rotate this out of the plane of the board, or we could rotate it within the plane of the board. So there's just 2, since it's not a 3-dimensional object. So U rotation is going to be 2 times 1/2 kT. So just kT. And so we've got 1.38 10 to the 23rd, 10 to the negative 23rd joules per Kelvin, and we're working at some specific, let's see, 350 kelvins. Okay, so we get 4.83, 10 to the negative 21 joules. Okay, so we did it, look, we wanted it for a single molecule, so there we are. All right, so now we've got a specific molecule, some sort of carbonyl. As you know, carbonyls vary depending on what type of carbonyl they are, but they're all roughly in that region of around 1700 reciprocal centimeters. And we want to know how many, if we look at a collection of these molecules, what fraction are in the first excited vibrational state instead of being in the ground vibrational state. And so to do this, we're going to use the Boltzmann distribution. So we'll call it N2 over N1 is equal to the difference, and actually I should write this a little differently. I'll say delta E, because I'm talking about the difference in energy between the two, over RT. And that's if we had a mole of molecules, but this is the energy of a single photon. So we want to put this on a molecular basis and not a molar basis. So we'll say negative delta E. I'll use a little epsilon to show that I'm doing molecular energies and not per mole. And that means we're going to have KT down here. Okay, so we have to figure out what that delta E is. So we can say delta E has to be equal to H nu. We could also say that's HC over lambda, since a wavelength and frequency have to multiply to give the speed of light. Or we could write it as a sort of strange notation here, where we could say reciprocal wavelength. Okay, and since that's what we're given, is reciprocal wavelength. And as long as we use the same units for distance in our reciprocal wavelength and our speed of light, we can just, they're going to cancel. So we'll do that. So we're going to plug this in up here. So we can put that in right there. Okay, so our ratio that we want is equal to negative HC reciprocal wavelength all over KT. And now we can just plug in some numbers. Well, actually, I'll put the equal sign down here. So we've got negative 6.626, 10 negative 34 joules times seconds. We've got the speed of light. And because our reciprocal wavelength is in reciprocal centimeters, let's put this into centimeters. So I'll say 3 times 10 to the 10th centimeters per second. And our reciprocal wavelength was 1700 reciprocal centimeters. 1700 reciprocal centimeters. And see, we can, that way we can cancel out those centimeters, cancel out those seconds. We're going to have joules on top. So let's see if we have joules on the bottom. We've got 1.38, 10 negative 23 joules per Kelvin. And the temperature was 400 kelvins. Okay, so we can see the kelvins cancel. We got joules on the bottom, joules on the top, which is good. We want the whole thing to be unitless. And we plug all that in, and we end up with 2.2, 10 to the negative 3 as our ratio. So basically, if we have 1,000 molecules with this carbonyl bond, and we're at 400 kelvins, which is quite warm. It's more than the boiling temperature of water. Only 2 in 1,000 are in their upper state. Okay, or rather, like if you have 1,000 that are in the ground state, you'd only have 2 in the upper state. So that shows you that basically thermal energy is not really enough to excite vibrations, the covalent bond vibrations at room temperature, even a little bit warmer. We'd have to go to more like thousands of kelvins if we really want to start exciting vibrations thermally. So when you shoot a sample with an IR beam to do your IR, most of your molecules, until they get hit by IR light, are actually in the ground state. Okay, average speed of argon atoms. This one's pretty straightforward. So we've got most probable speed, we've got average speed, and we've got RMS speed. In this case, I wanted the average speed. So sometimes we use the brackets because we tend to use the overbar, or I tend to use the overbar for per mole, so I use the brackets for average. So anyway, we've got 8 over pi, got our thermal energy up here, and we divide by the mass. And let's go ahead and put that in. So 8.314 joules per mole per Kelvin. We've got 400 kelvins. You've got this. Let's see. We want argon atoms, so that's 40. Now we got to be careful. That would end up being grams, so we got to convert that back down to kilograms. Okay, so now we've got everything in SI units, and it's not obvious how they cancel. Some of it's obvious. The kelvins cancel. This was kilograms per mole, so the moles cancel. But we have joules divided by kilograms. How's that going to give us our speed? So we can see the number we get. The number is going to be 460. And we think it's going to be meters per second, but we should check. So you should always check how your units cancel. So a joule, what is a joule? Well, just remember energy kinetic is equal to 1/2 mv squared, and then you can remember a joule is a kilogram meters squared per second squared. So you don't actually have to remember it as long as you remember at least one equation with energy in it, then you can remember what a joule is. So if you plug that in, we can see we've got the square root of joules over kilogram, and that's equal to, so we had a joule, a kilogram meter squared per second squared, and we're dividing that by kilograms. So we can see the kilograms cancel, and we've got meters squared and seconds squared, so it just gives us meters per second. So you should check that. Make sure you go through the mechanics. It's tedious, but it will make this will make sure that you don't sort of plug in some variable wrong or put it in the wrong side, or forget to go from grams to kilograms or whatnot. So highly recommend doing that. Okay, and the next one is ratio of oxygen gas molecules moving at one speed compared to another. And for this, since the distribution for speeds is the Maxwell-Boltzmann distribution, so we're going to use the Maxwell distribution here. So I'm going to simplify the Maxwell distribution. I'm going to say that the frequency of any particular speed is given by a constant times v squared e to the minus, and I'll put another constant, I'll call these C1 and C2, times v squared. Okay, because that'll show you that, oh, there's a lot of stuff I don't have to write, right? Because I can cancel those out. So we want a ratio, right? We want a ratio. So we want a ratio of speed 2 over speed 1. So we can say we've got C1, that's just our first constant, and then we're at speed 2. And we're speed 2 there as well. And then for the original speed, we'll call it V1. We've got that. And we've got e to the minus C2 V1 squared. And see, I didn't even need all this space. And oops, not the whole thing. So so then we can see, oh, we can just, that whole part at the start of the Maxwell distribution, that 4 pi over the quantity mass over 2 pi kt to the 3/2, we don't even need that, right? Because it's a ratio, so it's all going to cancel because there's no velocity in that part of the functionality. So we cross it off, save ourselves a lot of work. All right, so we can write this a little more neatly. We've got V2 over V1, that whole quantity squared. And we can see that we're dividing the top exponential by the bottom one. So we could write that. Remember, when you divide numbers with exponents, it's the same as taking this exponent and subtracting that. So we'll write that. So the upper exponent is minus C2 V2 squared, and then we're going to take this minus C2 V1 squared, and we're going to subtract it from the top, so we're going to lose that. We're going to lose that negative sign. Okay, so we could write this a little more neatly by pulling out the C2. So I'm going to pull out. I'll pull out a negative C2. Okay, so if I pull out negative C2, I've got V2 squared minus V1 squared. Okay, so that looks a lot simpler. We're going to have to plug in the actual C2. Notice we didn't have to bother with C1 because it cancels. So let's go ahead and plug in the actual numbers and the actual original constants. So we've got 600 meters per second over 300 meters per second. That whole quantity is squared, so it's just going to be 2 squared or 4. And then here we have to go and see what C2 is. So C2 was the bit of the Maxwell distribution that we just called a constant, right? So we had the mass of an oxygen molecule, which was, so I'll just write that up here. Mass divided by 2 kT. Or we could just as well say it's equal to the molar mass divided by 2 RT. Either one of those are fine. I think molar mass is nice because then you don't have to do any kind of conversion. So I'm going to use molar mass. So what do we have? We had the molar mass, which we said was, let's see, it's oxygen, so it's 0.032 kilogram per mole. We divide it by 2 times 8.314 joules per mole per Kelvin. The temperature, which we said was 450 kelvins. Okay, so our kelvins are going to cancel. The moles are going to cancel, so what we've got left is kilograms and joules. And then we've got the, we've got to put in V2 squared minus V1 squared. So we've got 600 meters squared, or let's see, 600 meters per second squared minus 300 meters per second squared. Okay, so I think that's everything. Let me check my notes. Yes, that is everything. Great. And so we plug all this in. We end up with 1.26. And the units should cancel. So let me just show you that they do indeed cancel. So this part's obvious. These cancel over here. What about this part here and this big mess here? So I already said that you can see the kelvins cancel and the per moles cancel. So we've got kilograms on top divided by joules. And then we have this leftover bit here of meters squared over seconds squared. Remember, a joule we said was a kilogram meters squared per second squared. So we can see the seconds are going to cancel, the kilograms, everything cancels, which is good because we're going to feed this into an exponential, so it had better be unitless. All right, so this is our final answer. So bottom line, there's more molecules moving at 600 than 300. Basically, that means that if we were to draw the distribution at 450 Kelvin, it will look something like this, and the average speeds are going to be actually in between those. It's going to be roughly 400-ish. So that's here. So what we're looking at is this must be say around 300, and this is probably at 600. So we got slightly more at the faster speed than at the slower speed. If we had chosen two speeds where they were both more than the average speed, then we know the higher speed would be a lower fraction, but that's not the case here. Number 12. Okay, so we need to find distance between collisions for a molecule. So in other words, the mean free path. So we can derive a formula based on either volume or pressure. Since the one in the equation sheet is given in terms of volume, let me just show you another one. You're probably already familiar with it. So we could say that the mean free path is basically how fast you're going divided by your single particle collision rate, so how often a single particle collides. And the single particle collision rate is just a function of the relative speed and the density, the number density, n over v, and the collision cross section. So basically, the more dense the gas is, the bigger the targets are, and the faster you go, the more collisions you have per second. And if you flip over collisions per second, you get seconds per collision. So that's how long you have between collisions. You multiply that by the speed. That's how far you can get between collisions. Okay, so let's go ahead and put those pieces together. So I don't want to put that there. So the mean free path, we said, is the average speed divided by zi. So this isn't the total collision rate. This is not zii or zij. This is for a single particle. Okay, so we're going to divide by this. So we get the relative speed, and we get the number density. Keep in mind v here, we're talking about volume, right? Actually, I'll just write volume just to emphasize that. Times the, so let's see if this makes sense. The bigger the volume per molecule, the further you can go before you hit something. Yeah, so I'm supposed to be dividing by zi. So actually, this should be on the bottom. Let's get rid of that. That is in the wrong place. Okay, so the bigger your target, the you can't go as far before you hit something. So all this makes sense, right? Because you're essentially dividing by how big your targets are. You're dividing by number density. You're dividing by relative speed. But given that, the faster you're going, the more distance you'll cover before you hit something. Okay, sounds good. So let's take this equation. And, oops, what just happened? There we go. Oh, I really went up high. Okay, so let's take this equation. Oh, darn it. Wow. Okay, so let's take this equation. Let's plug in some specific equations for the various speed. So the average speed, we know 8 over pi RT over mass, molar mass. We'll just leave that as volume. And the relative speed, the only difference is it's still 8 over pi, and this time we're going to plug in the reduced mass. So it's supposed to be a mu, but I'm going to do it per mole rather than per particle, and then RT. And you can see everything's going to cancel, most everything. And if we remember that mu for two particles that are the same is just the mass divided by 2, or we could say the molar mu is the molar mass divided by 2. So let's go ahead and replace this with the molar mass divided by 2. We can see that's going to cancel, and we just have a square root of 2 on the bottom. Okay, so we've got V over N over sigma, and we have a square root of 2 on the bottom. And at that point, what we can do is we don't have the size of our container, but we do have pressure, and we can see we've got V in this, and we can remember the physics version of PV equal RT is PV equal NKT, right? Because you're just doing everything on a counting up individual molecules basis. Okay, so to get V over N, we're going to divide, or both sides by N and both sides by P, rather, yeah. So we're left with V over N, and then we're going to divide the KT part that's left over by P. And we can push that in for this piece over here. So in that case, we're going to get lambda is equal to KT over P. And then we still have this leftover bit of the collision parameter, the collision cross-section, and the square root of 2. Okay, now we're ready to go. So we've got the mean free path, we've got 1.38, 10 to the negative 23rd joules per Kelvin. We are working at 320 kelvins. And we're also working at 25 bars, so we'll put this into SI units, 25 times 10 to the 5th pascals. And our collision cross section we said was 0.41. So it's 0.41 nanometers squared. So it's 10 to the negative 9th squared, so 10 to the negative 18th meters squared. And then we've got our square root of 2. Okay. Plug all that in, we get 3.0 10 to the negative 9th meters, or 3.0 nanometers. Okay, let's check the units just to make sure. So kelvins cancel kelvins. So what do we have? We have joules on top, we've got pascals, and we've got meters squared, and that's it. And there's a couple different ways we could go around checking these units. One idea would be to remember, well, there's a couple different ways we could do this. We could break it down into fundamental units, or we could do something a little faster, which is you remember that work is a negative integral of PdV. So if we take pressure and volume in units and we multiply them together, we should get work units. In other words, a joule is equal to a pascal times a meter cubed. So if we take that, we could put that in for our joule. We've got a pascal times a meter cubed, over a pascal times a meter squared. So the pascals should cancel, and that just gives you units of meters. And that's what we have. So the units do work out. Number 13, estimate the rate constant for reaction between two bromine atoms. We need to make assumptions. It's possible to do this problem without assumptions. So let's make the assumptions. We'll just say what they are. So first of all, we should write our master equation for simple collision theory for a rate constant between two identical substances. So this is built off the number of collisions between identical particles. And remember that we did that by multiplying the number density, if they were unlike particles, number density of particle A times number density of particle B. If it's identical particles, you take the number density and square it, but then you have to divide by 2 because you don't want to double count collisions, right? Because a collision between particle 1 and 2 is the same as a collision between particle 2 and 1. So you do have to do that when you have identical particles. That's where this comes from. So that's missing when you have collisions between unlike particles. Okay, we've got the relative speed, and we've got this activation energy term. Okay, so we can make some assumptions right away that they're actually really good assumptions. One is, let's assume that the activation energy is approximately 0. So if we think about this reaction, we've got a bromine atom with no bonds coming with a bromine atom with no bonds. There's an unpaired electron. Okay, so they're pretty high energy substances, and they're going to bang into each other and just form a bond. So we don't have to break any bonds to do this reaction. All we're doing is making a bond, so we expect the activation energy to be really, really close to 0. So if we do that, that means that our original term here is going to become 1. Okay, so that's a good assumption. The second thing we can assume is that the steric factor is approximately equal to 1. Why? We don't have to orient anything, right? These items that are colliding are spheres. So any collision angle is going to give us a possibility of a bond. So since they're both spheres, we can assume that. So that's going to be 1. So our expression is going to get much simpler. So say K is approximately equal to 1/2 Avogadro's number, collision cross-section, relative speed, and that's it. So let's go ahead and plug in those numbers. So we've got Avogadro's number 6.02 times 10 to the 23rd per mole. We've got our collision cross-section, and we're going to use 0.35. So 0.35 10 to the negative 18 meters squared. And then we have our relative speed. So I'll just plug in the equation for that. So 8 pi RT, and then we could plug in the molar reduced mass, or we could just cross that off and say that's the same as the molar mass divided by, that looks just, M and mu look a lot alike. The molar mass divided by 2. Since they're identical particles, we just say molar mass divided by 2. Okay, so we plug all this in. I'll make a note here that our molar mass is equal to, so remember, we're not doing, the things that are colliding are not bromine molecules, they're just bromine atoms, so it's just a single bromine atom, so it's just 80. So we put this as kilograms per mole, and the temperature was 375 Kelvin. Okay, so we plug all that in, and we get K is equal to 4.7 times 10 to the 7th meters cubed per second per mole. Let's check to make sure that we got those units. So let's see what we've got here. If we look at our unit check here. So we've got moles on the bottom from Avogadro's number. We've got meters squared on the top from the collision cross section. And looking at the relative speed, we take a shortcut here. We know this is the molar mass, and this is in joules per mole, so we know that cancels, and we know all this is going to come out to be meters per second. So we're going to shortcut that, meters per second, and so we can see we end up with meters cubed per mole per second. So that's good. All right, so now we can come down here and say the question statement did ask us to put this into more standard units for a rate constant. So liters per mole per second for a second order one. So we take our 4.7 10 to the 7th meters cubed per second per mole, and we do want to get rid of meters cubed and have liters, and we know there's 1,000 liters in 1 meters cubed. So we end up with our final answer, 4.7 10 to the 10th liters per mole per second, and that's our final answer. And if you look in the back of Atkins for gas phase reactions, you can see that this is a really fast second order rate constant, right? And it's because we have essentially a zero activation energy. So normally our rate constants for second order reactions are much smaller than this because the activation term is much less than 1 instead of being 1 as it is in this case. So that's the key for exam 1. Thank you for watching.